Kia ora koutou, no mai haere mai. Welcome to lesson 12 for introductory physics. As I said at the end of the previous lesson, this is not really to do with the forces and the motion and everything that we've looked at so far. This is slightly off on a little bit of a tangent. The reason we're introducing it now is because we'll come back to pressure after we've talked about the states of matter, solids, liquids, and gases, and introducing it now is just a good way for you to understand pressure in terms of forces that we can then build on that when we come along to looking at solids, liquids, and gases and building it up that way. So the goals are to, first of all, define density. That's just something that we'll need to understand as we talk about pressure. Then to look at how we calculate pressure for solids and within liquids. Then we're going to talk about atmospheric pressure. We haven't studied gases yet, but most people are familiar with the atmosphere because we live in it, that it's not too much of a stretch to understand that. And then we're going to talk about measuring pressure, so what gauge pressure means versus actual pressure, and specifically a device called a barometer for measuring pressure. So firstly, density. Density is just a measure of how densely packed in the matter that makes up an object is. If you have 1 kilogram of a solid metal, it might be a little cube, and it will have obviously a massive 1 kilogram, whereas to get 1 kilogram of something soft, like cushions, you'd have a lot more volume. Right? And the difference isn't their mass because they're both 1 kilogram. You have a big 1 kilogram cushion, it's going to be really big to be 1 kilogram. Block of metal to be 1 kilogram, it's going to be small. Right? The difference is not the mass, it's the density. It's how dense, how packed in all of that matter is. There's a whole lot, there's the same amount of matter overall, same amount of mass, still 1 kilogram in each object, but it's just more packed in for the very dense object. So density is just a measure of that. It is the mass divided by the volume, how much mass there is per unit volume. For density, we use another Greek letter rho, and it looks like a curvy P. A lot of the Greek letters look like curvy letters that we're used to because they're all originally derived from similar alphabets. So we've got the curvy letter rho, and it is just mass over volume. SI units are therefore going to be mass over volume, so kilograms over cubic meters. Dimensions ml to the negative 3. But density does actually have some other common units. So SI units are obviously the default, the standard that we all need to learn, but it is quite common to see kilograms per litre, litre being the volume in that case, or grams per centimetre cubed. They are both relatively frequently used, so do be familiar with them. Again, coming back to unit conversions, you want to remember how we did unit conversions and make sure that you're still on top of that because there will be some questions around that. Some examples, which I've noticed now have become unformatted and no longer aligned, but we've got iridium is the densest metal in this table, 22,000 kilograms per cubic meter. So first of all, imagine how big a cubic meter is. It's actually very large, right? Trace out 1 meter long, 1 meter high, and 1 meter deep. That's a cubic meter. That is quite a big volume. So if you have a block that big of iridium, it will be almost 23,000 kilograms. For platinum, 21, gold, 19, lead, 11, and so on down. You can see pure water at 4 degrees Celsius is 1,000 kilograms per cubic meter. Seawater is actually slightly more dense, 1,025 kilograms per cubic meter. And ice is less dense. As we all know, ice floats. It only has a density of only 919 kilograms per cubic meter. We will talk more about floating and about these different densities and especially about the density of water changing. You'll notice I've said at 4 degrees Celsius. It changes at different temperature. We'll discuss all of that, but that's going to happen in the second half of this course after we've talked about the structure of matter and we've talked about temperature and energies and all sorts of things. So for now, just the point of this table is that there's a big range of values of density. Weight density is something that's not very common. I will barely ever use it, but you should be aware of it just in case it does crop up in a question or a textbook or just something that you're interested in studying. Weight density is exactly the same idea, but it's instead of how much mass per unit volume, it's how much weight force is being applied per unit volume. So in this case, it's just weight over volume. Nice and exactly the same formula as our density for mass over volume. There's no symbol specifically for weight density. You'd normally just say that it's the weight density. As I said, it's not very common. There's no agreed upon symbol for it. On Earth, because the weight is just the force due to gravity of 9.8 times the mass, the weight density is just going to be 9.8 times the regular density. So now that we've got density out of the way, we can move on to the point of this lecture, which is pressure. We've already talked about forces and the idea that you put an object onto a surface, that surface will support it by providing a normal force, which is equal and opposite to the weight force of the object. The object now has no net force and stays where it is at rest. But let's look at the images on the right here. We've got an orange block thing. It's sitting on a shelf. In the top diagram, it is lying on a long side, and in the bottom diagram, it's standing on its end. It's the exact same block in both cases. The exact same weight force, the exact same normal force, but now we've got two different scenarios. And there is something different about them. You would hopefully look at that and realize that there's going to be a difference in the actual interaction that's going on between the shelf and the block. And that is that there's more of the shelf in contact with the block in the top diagram than there is in the bottom one. So if you draw a 1 centimeter grid over that shelf, just as an example, then every square of that grid that comes into contact with the object would be providing part of the normal force. Because the lying down block is coming into contact with a lot more of those squares, each square doesn't need to provide as much of the normal force. The standing up block is only touching maybe half as many, maybe a third as many of those squares. And so each of those squares will have to apply twice or 3 times as much force to the object. So the total normal force is the same, but the area over which that normal force is being applied is changing. And that's just what I've been saying. So this is the idea behind a bed of nails. You may have heard of a bed of nails. It's a common acupuncture sort of approach as well. There's actually mats you can buy that are like beds of nails, but they're with little plastic things called Shakti mats, and it's all the same idea. You can, if you stand on a single nail, it's going to go right through your foot. If you lie on a single nail, it'll go right through your skin. If you lie on a whole bed of nails, then that force, the total normal force to support you, is now being split up amongst all of those nails. And each one only needs to provide a fraction of the normal force to support you as a whole. And now that force is not enough to actually puncture the skin and damage you in any way. So you can quite safely lie on a whole bed of nails, but you can't just lie on a single nail. So this ratio of force over area is quite important, and therefore we've come up with its own name and terminology for it, and that is pressure. Pressure is just the ratio of force over area. So how much force is being applied per unit area? P equals F over A. The symbol for pressure is capital P. That's that P there. P equals F over A. So the block standing up will exert greater pressure on the shelf than the block lying down, and vice versa. The shelf applies pressure back up to the block. Just like Newton's third law, if there's forces going in both directions, there's pressure in both directions. Pressure is sort of described as being between them. We don't actually talk about pressure as having a direction. Pressure is caused by a force. The force has a direction, but pressure is technically just between the two objects. So the units for pressure, force over area, that's newtons per square meter. Because it is so common, we have its own special unit called the Pascal, with the letters PA, capital PA, as our symbol for Pascal. 1 Pascal is actually very small. 1 Newton per square meter. 1 Newton over 1 square meter is how we would get 1 Pascal of pressure. But 1 Newton is only about 100 grams. 100 grams spread out over a whole square meter. If you can imagine that, right? Very, very small mass spread out over a whole 1 meter. Not very, very small. 100 grams is big on some scales, but 100 grams is still small for our daily lives. Spread over 1 meter, that is very light. It's a very low amount of pressure. So 1 Newton is tiny. 1 Pascal is tiny, but we deal with pressures that are a lot bigger in general, as you'll see with atmospheric pressure. Atmospheric pressure is 101,000 Pascal. So just as we said 1 Pascal is very small, atmospheric pressure 101,000 Pascal is actually very large. Not huge, it's what we live in, but it is a surprisingly large amount. We don't often talk of pressure when we're dealing with solids because it doesn't really add anything to the scenario. If we've got a block resting on a shelf, we know the weight force of the block, we know the normal force by the shelf on the block's not moving. Discussing the pressure doesn't add anything to our understanding of the scenario unless the pressures become large enough to deform the solids, to actually squish these solids. So if you had a shelf that was made of some kind of foam, so if you had a shelf that was made of some kind of foam and you put the block on it, then that pressure is going to be enough to actually squash the foam shelf slightly, and then we would need to be concerned with the pressures and the deformation that occurs. We will talk about deformation a little bit later on in this course. We're not going to do that right now. But for that reason, a lot of the time what we do is we just assume the objects aren't being deformed. We call that being rigid, and we ignore pressure. We can just deal with forces. You may think, there's a little example there, you may think about how seating on grass or on dirt works in terms of pressure and forces. Seating for outside, for sitting on lawns, is specially designed. There's a little close-up in that bottom photo there that'll give you a bit of a hint as to what they do. So do think about that as a little thought exercise. Pressure in liquids is much more commonly utilized. Pressure in solids, as I said, unless they're deforming, doesn't add anything to our understanding. But pressure in liquids is always there because we can insert an object into a liquid. We can submerge an object underwater. We can submerge something inside some oil or whatever liquid we're talking about. We need to understand how the pressure changes right throughout the liquid because we can actually put things at those different positions inside the liquid. We can't do that for solids, but for liquids we can, so we need to understand how the pressure is changing right through that liquid. Suppose you're swimming in a lake and you put your head just under the surface. What sort of pressure is there from the water? Well, there's not going to be much because there's not much water above your head pushing down on it. If you're only just underwater, there might be just a thin film of water pushing down on your head. That's not a lot. So you're not under much pressure from the water. But if you swim down further underwater, there's now a lot more water above your head. So that pressure on your head or on you overall from the water above you is going to be increased compared to when you're only just below the surface. And if you go right down to the bottom part of the deepest part of the lake, then that pressure is going to be the greatest because there's the most water above you pushing down on you. And that's all pressure is. Pressure is just the pushing down or pushing on, doesn't have to be down, the pushing on something due to some other force, right? In this case, the weight force of the water being pulled down by gravity, that water is then pushing down on you. Pressure in a body of liquid is actually very simple to calculate, and this is why we had to meet the density before that we did. Pressure at any depth h in a body of liquid depends only on that depth h and the density of the liquid. It doesn't depend on the volume overall, just on the density and that height. So pressure is rho g h. Rho, the density of the liquid, times g, gravity, which is what's pulling that liquid down, times height, times how far underwater you are, or underwater the thing you're concerned with is. The textbook does use the formula pressure equals weight density times depth. As I said, I'm not a fan of weight density. Density itself is a very common unit and a very common, property, not unit, very common property. And rho gh is very simple to understand. It also means you can apply it to any gravitational scenario. You can go onto Mars or the moon and you can use this formula to understand pressure. So I don't like the limitation of using weight density times depth, but it is technically correct. You may wonder about the volume. So for this, I'm just going to jump over to the document camera and just describe something. We've got imagine you've got a really thin cylinder of liquid, right? So the liquid fills up the cylinder, and then you've got one that does this, right? And they're both to the same height, right? So the height overall is the same. And do you think that the pressure here is going to be greater than the pressure here? A lot of people will think it is going to be, but it isn't. It doesn't actually matter how much volume, even though this one has way more volume, this one has less volume, the pressure's the same at that depth. And that's because if you imagine drawing a little square, take some square and think about the area, the volume above that square. Think about the volume above that square, that column of water above that little square at the bottom. That is going to have a total mass. Remember that density is mass over volume. So if we know that volume and we know the density, then the mass is going to be density times volume. So we have a mass of density times volume. But the volume you can also think about as being this area times that height. So it's actually area times height. Density times area times height. That's the mass. The weight force then, so the force due to gravity of that column of liquid. I will point out now that I'm halfway through that this isn't absolutely necessary for you to learn this. You do have all the understanding to make sense of this, but I wouldn't expect you to be able to work through this fully and explain this completely to someone. But there's absolutely nothing stopping you from being able to. I just like to explain this for completeness. The weight force then is going to be the mass, which we've just said is density times area times height times gravity. Gravity, I did it backwards, I did a row, times gravity. So that's the weight force of that big column. So that's the force downwards on this square. But remember that pressure is equal to force over area. And we've just said the area is A, and we've just figured out the weight force. So that means we're going to have rho A hg over A, and those A's just cancel out. So yes, the total weight force does depend on the area because it depends on the volume, but the pressure also depends on the area, so the areas end up cancelling out, and you end up with pressure just being dependent on the density and the height and gravity, which again, assuming we're on Earth, is going to be constant. So the pressure ends up depending just on the height, not on the volume, assuming you are on Earth, it's going to have gravity in there as well. So as I said, you don't really need to know that, but there's absolutely nothing stopping you following what I just explained and understanding it. Let's talk about increasing pressure. You've got that block. Now we're sitting on a table, not a shelf, just because I felt like drawing a table. You're sitting on a block, sitting the block on a table, and then you add a second block onto the first block. The pressure between the bottom block and the table is now twice as much because it now is supporting twice the weight. That table is providing twice the normal force. We've got twice as much force over the same area. That means we have twice the pressure. P equals FA. If A is not changing, but F gets twice as big, P must get twice as big. So double the weight, double the pressure. This is true for any additional force. I used the example of putting a second identical block on top, but you could do any force. You could push down on the block. You could put a different type of mass on the block. You could do whatever you want to increase the force downwards on that block, which would increase the force onto the table from the block, therefore increasing the normal force back up and thus increasing the pressure between them. So you could increase that pressure any which way you want. And because the block doesn't deform, remember we're assuming there's no deformation, so the block doesn't squish as a result of the force you apply to it, that pressure is passed on, it's transmitted through the block onto the table. Because when you apply a force to the block, you are applying pressure to the block, and that pressure is transmitted through the block and increases the pressure between the block and the table as well. So there's pressure anywhere there's that force interaction. And the reason we talk about that is for fluid pressure. When you think about fluid pressure, which we were just saying is rho GH, then if there's anything pressing down on the top of that liquid, so whether it's a body of water or a glass of juice or a container of oil, if there's something pressing down on the top of it, that pressure is going to be transmitted through the liquid onto anything the liquid is in contact with, whether it's something submerged in the liquid or whether it's the sides of the container that are holding that liquid. That pressure will be passed on. So if you go and apply 10 newtons somehow to the surface of a liquid, it's quite hard to apply a pressure uniformly to the surface of a liquid. You'd have to have a liquid-proof seal over the whole volume of liquid that you can push down on and apply a pressure. Then that pressure would increase right throughout the liquid everywhere. But in most cases, there is something already pressing down on the surface of the liquid, and that is the atmosphere. The atmosphere, the air that we live in. The air that we live in is pressing on everything constantly, all the time, with what we were just saying before was 101,000 Pascal, 101 kilopascal. So that is always pressing down on the top of the liquid. Any liquid anywhere on Earth, assuming it's open to the atmosphere, has that pressure pushing down on it. That means that the pressure in the liquid is equal to the atmospheric pressure at the top plus the change in pressure due to that depth of liquid. So 50 meters down in this pool of water, the pressure due to the water is just rho GH, where we have rho for water, G for gravity, and H being 50 meters. That's the pressure due to the water, but the total actual pressure at that point is going to be atmospheric pressure plus the pressure due to 50 meters of water, because that atmospheric pressure that's pushing down on the top, that is transmitted everywhere throughout this column of water, and then all the way down. So right down, once you get all the way down to 100 meters, the total pressure is atmospheric pressure plus 100 meters of water pressure or liquid pressure. So you can figure that out at any height. You just have to remember that the total pressure is different from the pressure just due to the liquid. It's a good idea to keep both in mind, to calculate both. The pressure due to the liquid is how much more pressure there is that far down than there is at the surface, and that's still useful information. But the total pressure that far down is equal to atmosphere plus that extra pressure due to the liquid. The example here, we've got 1,000 kilograms per cubic meter, so this is pure water, which is realistic or not, we'll use it as our example. So 1,000 kilograms per cubic meter, the pressure due to the water at a depth of 1 meter is going to be 1,000 kilograms per cubic meter times 9.8 meters per second times 1 meter, which is 9.8 kilopascal. So 1 meter of water gives you a pressure due to that water of 9.8 kilopascal. But the total pressure is already going to be atmospheric pressure at the surface of the water plus that 9.8 kilopascal for going 1 meter underwater. So we end up at a total pressure of 111 kilopascal. So again, both are relevant bits of information. It's useful to know that going down 1 meter through water increases your pressure by 9.8 kilopascal. It's also useful to know that the total pressure at 1 meter below the surface of water is 111 kilopascal. Since the pressure in a fluid only depends on depth, not volume, and since the fluids transmit pressure everywhere, that's what we're saying. If you push down on the surface of something, it transmits the pressure through it. Liquids can flow everywhere, so they transmit it everywhere. So if you press down on it, it will transmit that fluid, that pressure everywhere. That means that if you have a connected body of water, then the pressure at any height must be the same everywhere. So you can see in that example, the top diagram, the two waters are at different heights, different depths. So the pressure along that grey dotted line is not equal. In the second diagram, even though the connection between the two bodies of liquid is higher up than our dotted line, the dotted line is going to be the same pressure everywhere because we have the same depth of water above the water at that dotted line. Doesn't matter if you're in the left side of the container or the right side, the height to the surface of the liquid is the same, so the pressure everywhere along that grey dotted line inside the liquid will be the same pressure. There's a little demonstration called Pascal's vases, and that is photographed there. The idea being that it doesn't matter how much volume or what shape the container is, the pressure being the same everywhere means that if they're all connected at the bottom, they will all end up being about the same height. The surface level is almost the same everywhere. There is a slight variation, and that's due to capillary action that we're not going to cover, which is basically the attraction between the liquid and the glass. They're sort of attracted to each other. Just this annoying thing for this photograph. If they'd made it slightly wider, it might have been more obvious, but they are essentially all at the same height. And that is because the pressure depends only on the depth, not the volume of liquid. The next part we're going to talk about is atmospheric pressure. We live in the atmosphere. The atmosphere is a big layer of air on top of the Earth's surface being pulled down by gravity. And just in the same way that being underwater means the water will exert pressure on you, the air is being pulled down by gravity. That's why it stays on Earth and doesn't float off into space. The air is being pulled down by gravity, and therefore it exerts a pressure on you because you're at the bottom of this big ocean of air. So everything under the atmosphere will be experiencing atmospheric pressure. And as we said, atmospheric pressure is 101 kilopascal. 101 kilopascal is 101,000 newtons per square meter. So draw out a square meter, mark out a square meter, if you've got a ruler or something, or just guesstimate a square meter. Atmospheric pressure is 10,000 kilograms pushing down on that square meter. And that's there all the time. That's on you right now. That's on your desk, on your computer. Everything that we do, our entire lives, lives inside this much pressure. 10,000 kilograms per square meter. Because it's perpetually present, all species have evolved in it. we don't notice it in the sense that we don't feel this pressure pushing on us. But we'd notice it if it changed significantly. If you go too far underwater, so it gets greater, then you would notice that increased pressure. If you go out into space where there's no pressure, then you would notice that and you would die. So we notice when it changes, but we don't notice that pressure constantly pushing on us because we're used to it. It's what we evolved in. It's a requirement for our species to function. Unlike liquid pressure, atmospheric pressure doesn't just depend on the depth of liquid because the density of the atmosphere is not constant. So for a liquid, the density is constant. It means it doesn't matter how far deep you go, you can just use ρgh. That's fine, the density doesn't change. But Earth's atmosphere does change. Right next to Earth's surface, the part where we spend most of our lives, the air is quite dense. But as you go higher up, as you go further up a mountain or something, for example, the air density gets less. There's actually less density. So that means we can't just use our ρgh and the depth of the atmosphere and figure out our pressure because it varies with altitude. That pressure change varies with altitude because the density is constantly changing. So we don't actually calculate atmospheric pressure at all. We will assume that it is always 101 kilopascal unless we're told otherwise, but we should be aware of the relationship, and that is not a straight line. So this top graph is a straight line between pressure and depth, and that is to do with going underwater. You can see that we start at 0, and if you go below sea level, the depth is just increasing and the pressure is increasing linearly. Getting all my adjectives mixed up. So the pressure is increasing linearly for something going underwater, but for atmospheric pressure, it starts out almost linear because the density near Earth's surface is fairly constant, but then it becomes less linear because the density changes and it actually curves. So you can see that the pressure starting at 1,000 millibar, which is an odd unit, but it basically means 101 kilopascal, drops down to 90 kilopascal. There, by the time you get to the top of Mount Everest, we're at 30 kilopascal, so a lot lower pressure. And then by the time you get up to, where are we? The altitude in kilometers is on the right. By the time you get up to 50 kilometers, then you're at very, very low pressure, right? Almost nothing. The atmosphere is almost gone. So the Earth's atmosphere is not a linear change in pressure. As I said, we pretty much just expect it to be 101 kilopascal, or we'll tell you if it's not. The last part is about measuring pressure. A pressure gauge is any device designed to measure pressure, but they all have one thing in common, and that is that they measure the target pressure compared to some reference pressure, right, relative to a reference pressure. That difference between the reference pressure and the target pressure is what we call gauge pressure. So any pressure gauge is a device that measures it, and gauge pressure is the reading that it gives you, but the reading will always be relative to some reference pressure. A common method is to compare the pressure inside a container to atmospheric pressure, to our standard 101 kilopascal. So we'll just have one end of our pressure gauge open to the atmosphere and the other one open to our target pressure, to our container, and we can take the reading and we know that whatever it says, it's that much above or below atmospheric pressure. So the reading itself isn't the actual pressure, it's the gauge pressure. It's the pressure difference compared to that that reference pressure. So tires on cars are a very common example. If you have a tire pressure gauge and it says 33 psi, which is pounds per square inch, pounds being a unit for force, square inch being a unit for area, so it is a pressure reading, pressure per square inch, but 33 psi is equal to 230 kilopascal. If your tire gauge says 230 kilopascal, that means that the tire pressure is 230 kilopascal above atmospheric pressure. The 230 kilopascal is your gauge pressure, and that means it's the difference between your target pressure and your reference pressure, reference in this case being Earth's atmospheric pressure. So it would be 230 kilopascal above atmospheric pressure. And that's useful information because that determines how the tire and the atmosphere will interact, because atmospheric pressure is always pushing on the outside of the tire. So the tire pressure inside being greater, how much greater it is determines how that tire will behave. So that's actually the bit of information we care about. But it's still important to remember that even though it's 33 psi greater than the atmosphere, the total pressure in there is therefore the atmospheric pressure plus 33 psi, or plus 230 kilopascal, which is around about 330 kilopascal. So even though the gauge pressure is the thing that we measure and the thing we care about and the thing we use in our daily life, the actual pressure is 101 kilopascal greater than that gauge pressure. Just a definition for you, a vacuum. I'm not talking about a vacuum cleaner. They don't actually produce proper vacuums. A vacuum is just the idea of no pressure. If you take a space, a container, and you take everything out of it, all of the atmosphere out of it, so it's literally empty. Not empty in the sense that we use in everyday life, where empty just means it's only got air in it. Empty meaning no air either. Empty meaning absolutely no matter in it. Then that's a vacuum. There's no matter, there's nothing to press on the inside of the container. The atmospheric pressure comes from the air pressing on us. That's what it comes from. If you take the air out, there's nothing to do the pressing, there's no atmospheric pressure. If you go out in space, same thing. If you go out in space, there's no air, there's nothing to do the pressing, so there's no pressure at all. So that's what a vacuum is in physics. A vacuum is just the lack of any kind of air pressure. That's a vacuum. A barometer is a device that we can use to measure atmospheric pressure, because we said a pressure gauge, a common approach is to measure it relative to atmospheric pressure. So how do we measure atmospheric pressure? We need some other reference pressure, and a common one is a vacuum. So to actually make a little space above, so this is liquid mercury, which is very common, make a little space above it inside a tube that is at 0 pressure at a vacuum. That way we know the reference pressure to be 0 Pascal. And we can use this to measure the atmospheric pressure. This uses 2 facts, both of which we've already met. Firstly, the pressure where a fluid meets the atmosphere is the atmospheric pressure at that point. So the pressure right at the surface of this liquid mercury, before you go under the liquid mercury at all, the pressure right at that surface is atmospheric pressure. It's exactly whatever the atmospheric pressure is at this location. Not our average 101 kilopascal that we're assuming. This is the actual atmospheric pressure at this exact location where the barometer is pressing on that liquid mercury. Since there is no atmospheric pressure inside this vacuum, the pressure right at the very surface of this liquid mercury is 0. So we've got 0 here, and we've got the atmospheric pressure here that we're trying to measure. The other thing we know is that the pressure along any horizontal line through a body of liquid is the same everywhere. So the pressure along this surface is atmospheric pressure, and if we continue along horizontally, the pressure anywhere along here must be atmospheric as well, that same pressure. Barometers are commonly made with a liquid mercury in an inverted tube with a vacuum above the column of mercury, as I've just been talking about. You can technically make it with other substances, but as we'll see, it's not very useful. So the pressure anywhere along that white dotted line is going to be atmospheric pressure. Here it's due entirely to the atmosphere, but at B, it's due to the column of mercury. There's no pressure from the vacuum, so we don't have to add on our external pressure. It's just the pressure due to that column of mercury. That's the only thing pushing down at B. And that means we can just use rho GH. So that means we know that the pressure at A is equal to the pressure at B. The pressure at A is equal just to the atmospheric pressure. It's due to the atmosphere. The pressure at B is equal just to rho GH. It's due to that column of mercury. So we have the atmospheric pressure is equal to rho GH. So the point of a barometer is that you can measure the height of that column of mercury, and from rho GH, you then know exactly what the atmospheric pressure is outside here at point A. That's how a barometer works. For a mercury barometer, the density of liquid mercury is 13,600 kilograms per cubic meter. It's very dense compared to water. To figure out how big we need to make our barometer, we're going to use our 101 kilopascal as our estimate of what the pressure might be and see what the height of mercury would be in that case. And so we just rearrange that equation. If the atmospheric pressure is equal to rho GH, we just rearrange it to get H is equal to atmospheric pressure divided by rho G. Remembering that we're using liquid mercury, not water, for our density, and we get a height of 0.76 meters. So a barometer needs to be 76 centimeters tall. We do have one in the physics lab here on the Manawatu campus, but obviously this is a distance course, so you won't get to see that. If you do physics at Massey in future, you may get to see that barometer and in fact use it in some of our labs. So a 76 centimetre tall column of mercury will be enough to tell us the pressure. Obviously you allow some change, some room for it to get higher or lower for the atmospheric pressure to change. You can then read the change in height and know what the pressure is. So other liquids would work, but if the density decreases, so if you make density lower, you can see that height is going to get bigger. So if you get a less dense liquid than mercury, then you are going to have a much higher column that you need. If you do it with water, it ends up being something around 10 meters tall. You would need to make a 10 meter tall barometer for that to work, which is not very practical. Finally, on the same vein as a barometer, which measures atmospheric pressure, if we know how atmospheric pressure changes with altitude, then we could use a barometer to tell us the atmospheric pressure and then basically read off a chart to tell us the altitude, how high above sea level we are. A device that just does that, that's all built in, is called an altimeter. So altimeters are basically barometers for measuring atmospheric pressure, but have a built-in conversion on the readout that tell you the altitude instead of the pressure. That's the end of this lesson. As I said, we will come back to pressure. This was sort of a little intro, and then we'll come back to it after we've talked about solids, liquids, and gases, and hopefully all of this will make a bit more sense. But I do expect you to be able to understand this at the moment. Okay, there is, I believe, there's a couple of questions on the assignment about it. So you should be familiar with all of this. You don't need to worry too much about the details and the why it's happening, where atmospheric pressure comes from, any of that kind of stuff. But understanding what density is, what pressure is, how we calculate it, and the idea of pressure being transmitted through substances. You apply a force to the top of a block, the pressure that you apply is transmitted through the block to the surface between the block and whatever it's sitting on. So do hopefully get to grips with all of that. But as I said, we will come back to it. We will revisit pressure and obviously density along the way.